Welcome to another episode of Dominic Does DIY. As always, like, subscribe, and comment down below if you find this entertaining or useful. Also, if there's something that you would like to see or explained, let me know in the comments down below. So now let's get on with it. Just as an update on the HUD I was working on from the last video, I was actually able to see in my firmware and why the course was not accurately being displayed and overwritten with my backdrop. So I will update more on that as I keep working on it, and hopefully I'll be able to show you guys some full operational use inside the truck later. However, today we are going to do another challenge. We are going to be investigating a voltage doubler. What we have is a 5 volt supply, and we need a 9 volt to 10 volt supply for a buzzer that requires 15 milliamps of supply current. Since we don't want to add a whole boost circuit for this small amount of energy, we want to implement a voltage doubler. After looking up some basic information, you find a bunch of data online, but the majority of the information you review is for an AC circuit. Even though you are not using an AC circuit and we have a DC circuit, you wanted to implement this on the simulator so you can kind of understand how the voltage doubler is working, at least in the AC application. So when you see the system, it is just 2 caps in series to supply the output. During one half of the cycle of the AC input, you go through D1 and charge C1, and D2 prevents current flow from the supply through C2. And then on the second half of the cycle, it reverses. So current flows through D2 and allows C2 to charge, and current is prevented from flowing through C1 due to D1. So you're alternating the charging of the caps and supplying the load with the sum of the voltages on C1 and C2. So you can see how the output gets a voltage bump every time one of the caps goes through a charge cycle. So now you understand how this is working, you have to understand how to get it to work with DC, not AC. After all, we will have a 5 volt DC supply, not an AC signal. You do some more digging and you find a simple modification of the caps and diodes achieves the same result, except they use a clock signal as the trigger to charge/discharge the cap. So here we are really only charging up one cap, the C9, to get the double effect. C8 is just an output power supply cap. This will actually supply the load with all the energy, and all we're really doing is going to be charging that capacitor. When the clock is 0 volts, C9 charges and is charged to VCC minus the voltage drop of D7. Then when the clock goes high, the voltage at C9 is now clock voltage plus the VCC minus the forward voltage drop of D7. And since the clock will be ran by VCC, it is pretty much 2 times VCC minus VF. During this time, D7 prevents backfeeding to the VCC rail from the cap, so all energy can supply recharging of C8. And you can see here that every time the clock pulse goes high, we can see that output voltage on the Vout DC rail, it goes high with every pulse. You need to replace the clock, this V4 here, with some hardware to excite the circuit to give us our output. And we don't want to supply power from the clock itself as this circuit is doing. So right now the clock is your base VCC, and that output then gets added to the voltage on C9 to give us our output for the doubler, but we don't want that. We want to actually supply the base of that C9 with VCC. We want all energy being supplied from the system, from the VCC rail, and not the clock signal. The clock signal itself is just going to be a nothing burger. It's just going to be a signal that uses really no current whatsoever, well, minimal amount of current, but not feeding the actual system. So in order to do this, you are handed the following parts to make it work. You are handed 1 PMOS, 1 NMOS, 1 op amp, and you have a resistor and capacitor kit with no limits here. So you can use whatever resistors and capacitors that you want. So pause the video now if you'd like to try and solve the problem. Otherwise, continue on and I will go over the solution. First things first, let's look at how to charge the cap and then supply VCC in series with the cap so that we can generate the doubler circuit. By placing the PMOS and the NMOS in this configuration, when the PMOS M1 is on, it will supply the base of C4 and will be in series with the capacitor. So we will get the VCC plus the voltage drop on C4 for the output. And D3 will allow the voltage to be higher at this point than VCC. And when the NMOS is on, M2, it will allow the cap to charge through D3, and the body diode of M1 will allow C full to fully charge to VCC. The one downside of this, just off the bat, is we are going to ignore the fact that we could have a possibility of shoot through here. We're going to ignore that in this video. But whenever you're turning on a PMOS and an NMOS with the same signal, depending on the characteristics of the FET, you could end up with the PMOS and the NMOS momentarily being on, and this is what is called shoot through. So as you can see, if both of those components are on at the same time, we'll basically have a direct short to ground from VCC, and so we can end up damaging those MOSFETs. We will not take that into consideration in this video. Maybe in a future video, I'll go over shoot through and how you can design for that. So you can see here in the output, when the clock is high, and the clock is the yellow line, C4 is charging, and you can tell C4 is charging because the current through C4, which is the blue line, you can see that its current is going from 0 amps all the way up to 1.6 amps. And when the clock is low, C4 is discharging and charging C3. So we are switching and doing what is necessary to generate our voltage on the output. Now all we have to do is work on the clock signal. Because we don't have a magical VDC clock signal like here in the simulator, all we have is an op-amp and some passives. We have to do something with that in order to generate this clock signal that we're seeing down here. So for the clock signal, we're going to use that op-amp, and we're going to set it up as a comparator with some hysteresis. As we know, for a comparator, the N plus, when the N plus is greater than N minus, then the output is high, and opposite, right? When N plus is less than N minus, then the output is low. For this, we will be setting our bias control voltage to the N plus pin, and then our time delay input on the N minus. So that's what you can see here. You can see that our N plus is being held by our bias from the feedback resistor. We got an input resistor, and we've got our ground resistor here, and we're going to consider this our bias. And this is our time delay circuit right here, which is going to be feeding our N minus. So we know that the op amp, since it's a comparator, we've got two output possibilities. It's either going to be one of the two rails, either ground or VCC. And so when the output of the op amp is 0 volts, R5 and R6 are in parallel. So the formula for N plus is equal to VCC times R5 in parallel with R6 divided by R plus R5 in parallel with R6. And we're going to call this one the lower trip point. Now when the output of the op amp is 5 volts, then R4 is in parallel with R5, and N plus is equal to VCC times R6 divided by R4 in parallel with R5 plus R6. And we're going to call this the upper trip point. In addition to this, we need to then calculate the RC time constant, R3 and C5, the R and the C, because when the output is 5 volts, we will be charging the C5 cap, and when the output is 0 volts, we will be discharging the cap. So N minus will basically be swinging between the upper trip point and the lower trip point. So we know that the capacitor charge time formula is V capacitor equals the supply voltage times 1 minus E to the minus T over RC. So when we solve for T of the charge formula, because that's what we care about, is we want to know how much time this takes, T equals minus log, natural log of 1 minus VC over VS times RC. So for us to know the time it takes to charge to the upper trip point from the lower trip point, it is just the time it takes to charge from the upper trip point minus the time it takes to charge to the lower trip point, because the charge thing is always from a state of 0. So there we go. And for discharging, it is a little more direct because the formula is V cap, the voltage across the capacitor is equal to the initial voltage times E to the minus T over RC. And so rearranging this formula gives us T equals negative natural log of V, the capacitor voltage over the initial voltage, times RC. So we know these, we know the capacitor voltage and the initial voltage because the initial voltage is going to be our upper trip point, and we know the end value of VC, the capacitor voltage, because that is our lower trip point. So on this one, we just need to solve for T using those as our values. So in order to do all this math, I just made a spreadsheet to do it all so I can play with the values and whatnot. That's how I came to these values. But you can see from my spreadsheet here, using the formulas, I calculated my upper test point here and my lower test point here using those formulas. And I can also calculate the time that it is in the upper test point region and the time it is in the lower test point region. So, and that's again based on R and C. And I was able to calculate also, once you got this, then it's easy to just calculate some duty cycle and some frequency. But you can see using these values, our upper test point, our N minus, will bounce between the upper test point and the lower test point. So 2.91 volts and 2.08 volts is what we'll see on the N minus pin, just kind of bouncing up and down as the cap charges and discharges. And we should see on the output of OPA clock there, over here, we should see the output at about a high and a low at these times. So we should be running about 3 kilohertz, and we should be seeing it high and low for 168 microseconds roughly. So let's go ahead and run this. Let me just zoom into a little section right here. And so you can see here in minus, you can see the cap charging and you can see the cap discharging. And you can see that it's bouncing and it's charging and discharging to the upper and lower trip points, which is this blue-purple line right here. And so what are those values? Well, our upper trip point, if we look at that, our upper trip point is sitting right at 2.91 volts, 917, which is what we had calculated. And our lower trip point is 2.08, which is exactly what we calculated. So we can just bring that up. So it's 2.91 and 2.08. And just so we can get another feel good on that, you can do that. And you can see 2.917, 2.083. And you can see it is really close to the math that I calculated, which would make sense, right? Because all simulators do is math. And then it was 168 microseconds. So if I put that right there, and I bring in a second cursor, bring that over here, and you can see that our difference between cursor 1 and cursor 2 is roughly about 170 microseconds, which is exactly what we were expecting for the on time. And if I just take this and move this over to the off time, you can see again 172 microseconds of off time. So roughly about 170 microseconds on and off. So a 50% duty cycle, which is exactly what we were looking for. And if I go over here to see the frequency, you can see we got about 2.9 kilohertz, and I calculated out at about, I think that's actually what I calculated out, was 2.9. I just rounded up to 3. If we bring that back up, you can see here 2.972, and so you can see here it's about 2.9 kilohertz. So pretty close, pretty close. So we can see that our clock cycle does exactly what we want with this op amp, with the hysteresis and the auto oscillation. And all I had to do was supply it with the VCC right here. So if I zoom, make this a little bit bigger. And so this VCC, it really is just 5 volts, but there's really no current on it. So if I wanted to make this an enable pin from a micro or something else, I could just turn it on. But right now I just have it connected to VCC to have it go. And then ultimately we wanted to make sure our output met our spec. Oh, let's just bring this all into, whoops, didn't want that. Let me hit the right button here, go here and do that. And so you can see that we have here, remember it was between, I wanted to stay between 9 and 10 volts. So you can see right here, our low point is going to be 9.18 volts, and our high point is about 9.3 volts. And if we go up here and we do the current, you can see that my current here, I through R7, this is our load. This would be considered our buzzer. We said we wanted to be able to push at least 15 milliamps. And you can see here at 500 ohms, we're actually pulling more than 18 milliamps based on the chart over here. So I've got plenty of headroom. The only thing that'll change on this is the max voltage really won't change. All that's going to change is if I change this resistor and make it closer to 15 amps, the discharging of C6 will be less severe. So instead of the peak will be the peak, there's nothing I can do about that, but the low end, instead of being 9.18, if I'm only pulling 15 milliamps, it may only pull down to like 9.27 or something like that. So that's all I have this time. Thanks for watching. I hope you enjoyed the video and learned something about voltage doublers and oscillators. And thanks to all who have subscribed and shared, and I'll see you next time. Have a good one.